Hello everyone, this is Lecture 8 of ComSci 142, Graph Algorithms. In the first part of this video, we will discuss what graphs are, how to represent them, how to do graph search, and how to do tree traversals. We won't be talking about this type of graphs, so it's not bar graph or line graph or graph, get it? But it's this type of graphs. So I'm sure you've seen this type of graphs before. Okay? So formally, a graph G is made up of two components, V and E. So what are these two components? V is the set of vertices or nodes, and this represents objects. On the other hand, E is the set of edges or arcs that link two vertices together. So an edge is always a vertex pair. Okay? And graphs represent pairwise relationships among objects. So if you have your vertices as objects, the edges that link them together represents their relationships. Okay? Now, this is a pretty standard notation. We use n to represent the number of vertices and m as the number of edges. So later on, when we talk about the running time of graph algorithms, we will express them in terms of n and m. And that is important for you to follow the standard notation because everyone else is using that. So don't interchange the two because you'll confuse other people. Okay, so again, n is for vertices, m is for edges. Okay, now for the two main graph flavors, we have directed graphs and undirected graphs. A directed graph is when the edge is an ordered pair, and that means that A is going to B. Okay, so the order matters. A first before B. So A is the source, B is the destination. Whereas in undirected graphs, edges are unordered pairs. So it could be AB or BA, it doesn't matter. But in directed graph, this is an edge AB and this is not an edge BA because BA should be going the opposite direction. Okay? So, okay, let's try to figure out what would be the limits for the number of edges within a graph. So let's say you have a connected graph, meaning everything is connected, no vertex is left alone, and it's undirected, so meaning there is no direction with the edges. And let's say that there are n vertices and no parallel edges. When we say parallel edges, it just means that you have let's say something like this, like A and B, and then you have two edges that link them together. So this is a parallel edge. Okay, so assuming that there are no parallel edges, what would be the minimum number of edges and what would be the maximum number of edges? Okay, so for this type of graph, your limits are actually your best case is n and the worst case is n squared. Okay, so m is in omega of n and it's also in O of n squared. So the minimum amount or number of edges would be if you have one edge per vertex. Okay, so that if you have one edge per vertex, then all of them would be connected. Okay, so that would be omega of n. And then for the maximum, that would be if the vertex has each vertex has an edge to all other vertices. Okay, so we'll actually see this specific type of graph later on, something called a click. Okay, so if it has an edge to all other vertices, that would be in O of n squared. Okay, so again, the number of edges ranges from n to n squared. Okay, now let's take a look at some special graphs. So the chain network is one wherein you have n vertices and n minus 1 edges. So this is the bare minimum to make the graph connected. Okay, so the each vertex has one edge. So this one has this edge, this one has this edge, this one also has this edge, and this one has this edge. Okay, one or two edges. So n minus 1 edges in total. So this is like a chain, right? After that, you could also have a ring network wherein you have n vertices and n edges. So they now form like a loop, a ring. Okay, Next is a click, wherein you have n vertices and n times n minus 1 over 2 edges. So a click is when you have each vertex being connected to all other vertices. Okay? So if you look here, this vertex is connected to this one here, this one, and this one. And then the rest is also connected to all the other vertices. So this is a click. Okay? All vertices are connected to each other with an edge. Next special type of graph is a tree. Okay, so we'll talk more about trees later on. So in a tree, it's connected, so meaning there are no disconnected vertices, and there are no cycles, so it's a cyclic or a cyclic. Okay, so you've probably seen trees also in the past, so like binary trees, okay, recursion trees, and so on. Now, let's go through some graph terminologies, some words that we need to know in order for us to talk about graphs better, and we're on the same page with what they mean. Okay, so first is neighbor. So when we say that two vertices are neighbors, that just means that there is an edge between them. So if UV is an edge in the graph, then U is a neighbor of V and vice versa. Okay, so they are neighbors if they have an edge between them. The degree of the vertex is just the number of neighbors the vertex has. Okay, so it will tell us how many neighbors it has, or the number of edges going to the vertex. So if you have something like this, so the degree of A is 3 because it has 3 edges. B only has 1, C has 1, D has 1. Okay, so that is degree of vertex. Next, a graph is called a regular graph if each vertex has the same degree. Okay, so an example of this is a click or a ring network. So if you have a click, something like this, so remember that in a click, everything has to be connected to each other, right? So this one is a click. So this one has a degree of 3. This one also has a degree of 3, 3, and 3. So since all vertices have the same degree, this is a regular graph. And then for the ring network, it would look something like this, right? If there were 4 vertices. So this one has degree of 2, 2, 2, and 2. Okay? Now, for 3 vertices lang, this would also be a click and a ring network. Okay? It's a click because it's connected to all the other vertices, and then it's also a ring network because it has n vertices and n edges. So this one has degree 2, 2, and 2. So this is also a regular graph. Okay? Now for predecessors and successors, this is more used when we have a directed graph. So if UV is a U to V is a edge in a directed graph, then we say that U is a predecessor of V and V is a successor of U. So the source is the predecessor of the destination, and the destination is the successor of the source. Okay? So just some terminologies. Then we also have in degree and out degree. So for in degree, this is just the number of predecessors. Okay, so the number of edges going into the vertex. And then the out degree is just the number of successors, or the number of edges going out of the vertex. So if we have a graph, and let's just zero in on one vertex, let's say in vertex A, it has edges going there, and then something like this, for example. So the in degree of vertex A is how many? 1, right? Because there's only one edge going in, which is this one. And then the out degree would be 2, because there are 2 edges going out. So this one and this one, right? So that would be in degree and out degree. So your specifying or yeah, you're specifying whether it's an in degree or an out degree, not just degree of vertices in undirected graphs. Okay, next we have a subgraph, which is just another graph H that uses V prime and E prime as its vertex set and edge set, and it's a subgraph of G if the set of vertices are a subset of the original graph's vertex, and the set of edges is also a subset of the original set of edges. Okay, so you're basically taking like part of the graph, a subgraph. Okay, and then a path is just a sequence of edges that or we're in that sequence of edges, the successive pair of edges share a vertex. So later on, we will see paths when we talk about shortest paths, okay? But let's say that we have a graph like this. So let's say this is A, B, C, D, E. So we could have a path from A to E being A, B, D, E, right? So this is one path from A to E because you go from A, go to B, go to D, and then go to E. So this is the path. Or another path would have been A, C, D, E, right? If you chose the bottom path, A, C, C, D, and then D, E. So this is also another path from A to E. So that is a path. Okay? So you'll notice that the successive pair of edges share the vertex. So you cannot jump from one vertex to another in a path if there are no edges between them. Okay? Next, a connected graph is when there is a path from any vertex to any other vertex. Okay? So you can reach any vertex from another vertex. Okay? There is no isolated or island vertices. So we'll see this in the second part of the video when we talk about connectivity. Okay, and then another type of connected graph is the strongly connected graph, and this time we use this for directed graphs. So because for connected graphs we can apply this for mostly for undirected ones. Okay, so we don't care about the direction. But if it's strongly connected, we consider the direction of the path. Okay? So, it's a strongly connected graph if there is a directed path from any vertex to any other vertex. Okay? So, we will see this also in the second half of the video when we talk about strongly connected components. Okay. So, next, we also have graph components. And this happens when we have a disconnected graph. So a disconnected graph is when, so earlier we said that a connected graph is when there is a path from any vertex to any other vertex, right? But if that is not possible, then it's disconnected. So there are some vertices that you cannot reach from other vertices. And if that is the case, if it's disconnected, then the graph components are your maximal connected subgraph. So which parts are connected? Okay, so if we have multiple parts, which parts are the most connected out of the subgraphs? Okay, so we will also see this later in the second half, but technically we define this as follows. So two vertices v sub 1 and v sub 2 are in the same component if there exists a path from v1 to v2. Okay, so they are part of the same component, but if you cannot reach v1 to v2 or v2 to v1, then they don't belong to the same component. Okay, so we'll see this later. Next, we also have something called a cycle. So a cycle is a path that starts and ends at the same vertex. So pretty much it ends up where it started. Okay, but it also needs to have at least one edge. Sorry. So for example, if we have a graph like this, so A, B, C, D. So one cycle path here is A, B, D, C, A, right? So AB, BD, DC, and then back to CA. So it started and ended with the same vertex. Okay? But it also needs to have at least one edge, because if you say the path is just A, this is not a cycle. Well, it started and ended at the same vertex, but it needs to have at least one edge. But this doesn't have any edge, so this is not a path nor a cycle, right? So it needs to have at least one edge. And then after that, we have directed acyclic graphs, or DAGs. Okay, we call it a DAG because it's the initials, directed acyclic graph. So it's a directed graph with no directed cycles. Okay, so we'll also see this later in the later part of the graph algorithm discussion. Okay, and then in shortest paths also, we'll also see this in DAGs. Okay, so next we have something called a spanning tree. So a spanning tree is just a subgraph which is a tree. Okay, so it contains all vertices and it can only exist if the graph is connected. So we will actually see this more in the next video when we talk about minimum spanning trees. But basically, it's a tree that spans all vertices. So meaning it's a collection of edges such that all vertices are covered at least once by the selected edge. Okay, so yeah, we will talk more about this in the next video. So this can only exist if the graph is connected, because of course you cannot reach all vertices if one of them is unreachable, if it's disconnected. Okay, now if that is the case, if it's disconnected, then we won't have a spanning tree but a spanning forest. Okay, a spanning forest is just a collection of spanning trees, and you have one spanning tree for each connected component if the graph is indeed disconnected. Okay, so we'll also talk more about this next video. Okay, so now that we're done with the basic graph terminologies, let us now look at some more graph flavors. So we will distinguish between these types of graphs. Okay, so we've already seen undirected versus directed earlier, right? So again, in undirected graphs, the edge xy just means the same as edge yx. So the direction does not matter. Okay, so it's an unordered pair, vertex pair. But in directed, order matters. So edge xy just means that you have an edge going from x to y. This is not the same as edge yx, because edge yx would be from y to x. It should be in the opposite direction. Okay. One example of this would be highways and city streets. So for highways, you could think of this as undirected edges, because usually it's two-way, right? If you model highways, then usually it's undirected graph, because you can get from A to B or from B to A with no problem. But if you are modeling city streets, you cannot immediately make this undirected. You have to make this directed. Okay, why is that the case? Because although it's true that in some city streets it's also two-way, so you'll just model it like this, right? So there is a directed edge from here to here, and also a directed edge in the opposite direction. So this is if it's two-way. But usually in city streets, there are one-way streets. So to model that, you have to specify the direction. Okay, you cannot simply use undirected edges, because this will mean that it's automatically two-way, when in fact some streets in the cities are one-way, right? So you need to have a direction. Okay, so that is directed versus undirected graphs. Next, we have weighted and unweighted graphs. In weighted graphs, the edges or vertices has a specified weight. So later on, in some applications, we could see some edges with associated weights, okay, some numbers, or it could also be that the vertex has an associated weight. Okay, so either the edge or the vertex has a weight. So an example of this would be sample applications like for modeling roads. The weight could be either the length of the road, or the driving time, estimated driving time, or the speed limit, right? So you could model however you want, depending on the application, but the weight itself depends on what you use it for. Okay, but it's just a number that's associated with the edge or the vertex. Okay. Otherwise, if there are no associated weights, then the graph is called unweighted if it has no cost associated with the edges or the vertices, or the vertices. Excuse me. So, if that is the case, we also call it a uniform cost graph, because basically you can think of the edges as having equal cost. Okay. Yeah. So, okay. So we have an example scenario here. Let's say that you're a fugitive. So sorry for these examples wherein you're having a life of crime, like when we did knapsack problem, you were a robber or a thief, and then now you're a fugitive. But again, I'm not promoting a life of crime here. It's just how the examples were created. So anyway, just imagine that you're a fugitive who wants to go from town A to town E. Okay, and you want to go through towns with the least police encounter, right? So what would be the underlying graph in this problem? What would be the nodes? What would be the edges? And what would be the weights? Okay, so try to think about the situation first before going forward with the video. Okay, so for this one, the nodes would have to be the towns, right? So town A, town E, and then the other towns within the province. The edges would be, of course, be the roads. Okay, and then what would be the weights? Well, you could put the weights on the towns itself because you don't want to go through towns with the least police encounter. So the weights could be placed on each node, and the weight itself would be the number of policemen in that town. Okay, so that would be the underlying graph. Okay, okay. So that is excuse me, that is weight. Next, we have simple versus non-simple graph. A non-simple graph is when you have self-loops wherein the edge goes from X going back to X, or if you have multi-edges like a parallel edge. Okay, so the edge XY occurs more than once. Okay, so example of a non-simple graph is when it has self-loops like this. So it goes from A back to A, or if it has multiple edges like A, B, and then there are multiple edges or multiple connections that connect them. So this is known as the parallel edge. Okay, so if either one of the two are present, then it's already non-simple. Okay, otherwise it's simple. Next, sparse graphs versus dense graphs. So sparse versus dense talks about the number of or the fraction of vertex pairs in comparison with edges. So how many edges are there compared to the vertex pairs? Okay, so that just means that in simple terms, do you have a lot of edges? Okay, if you have a lot of edges, that's dense. Otherwise, it's sparse. So if it's sparse, the number of the fraction of vertex pairs with edges is just small. Okay, so it's about O of n. Okay, so the number of edges is almost the same as the number of vertices. So there are only few edges. Whereas if it's dense, there's a lot of edges. Okay, wherein m is in O of n squared. Okay, so it's almost it's polynomial in terms of n. So that is the distinction between sparse and dense graphs. Okay, next we have cyclic versus acyclic or acyclic. So acyclic just means that you don't have any cycles, and then cyclic, of course, there is a cycle in a graph, at least one. So a tree is an example of an acyclic graph, and it's also connected. Okay. Okay. Excuse me. Next, we have labeled versus unlabeled graphs. So a graph is labeled if the vertices have names. Okay. Otherwise, it's unlabeled if the vertex has no identifier. Okay. So if you just have like nodes without labels, then it's unlabeled. Okay. Now let's take a look at a specific type of graph called the friendship graph and apply the different flavors to it. Okay. So okay, if you ask this question, if I'm your friend, does that mean you're my friend too? What graph flavor is this talking about? So this is talking about undirected versus directed graphs, right? So for example, in Facebook, it's an undirected graph because if I'm friends with person A, then person A is also friends with me. But in Twitter, for example, it's just a directed graph because if I follow A, that doesn't necessarily mean that A follows me back. I mean, if we know each other, it's probably common courtesy to follow each other back. But yeah, it's not necessarily the case, right? So if you follow some person, it doesn't necessarily mean that he'll follow you back. So it's just directed graph. Okay. Next, have you heard of someone? Okay. Is this directed or undirected? Have you heard of him? This is directed, right? Because I've heard of Angelina Jolie, but she's probably never heard of me yet, right? So this is a directed graph. It's a one-way street. Kissed with graph. Is this directed or undirected? Well, depending on the type of kiss, this is probably undirected. Okay, so because I can't be kissing someone and he or she is not kissing me back, right? Unless it's an imagination. Anyway, but usually this is undirected because it takes two to tango, right? Anyway, so next, how close of a friend are you? Okay, what type of graph flavors is talking about? So this is talking about the weighted graphs. Okay, so you could weight them as follows. So if you're enemies, you could give it a weight of -10, and then if you're BFFs, you could give it a weight of 10, and then if you are neutral or strangers, you could give it a score of 0, right? So the closeness could be represented with the weight of the graph. Okay? Am I my own friend? So this refers to self loop. Okay? It's a simple graph if there are no loops. And then you could also have multiple edges, like you can connect or you can put two edges between x and y to represent two different relationships. Like x and y could be connected because they are college classmates and then they are also neighbors in their hometown. So there could be two edges connecting x and y. Okay, so that won't make it a simple graph. This would be a non-simple graph if there are multiple edges. Okay. Who has the most friends? So what part of the what part of the graph should you look at for this one? Okay, so to find out who has the most friends, you need to look at the node with the maximum degree. Just remember, the degree of the node is the number of edges connected to it. Okay, so yeah, that would tell you who has the most friends because it has the most number of connections. Now, for a barkada, you could model that as a dense graph because mostly all of the people there are connected to each other. So there will be a lot of edges. But if it's a bunch of strangers, that's probably a sparse graph because there would only be few connections, if any, right? So yeah. Okay, next. Are you a distinct individual or just part of the faceless crowd? So this talks about whether the graph is labeled or unlabeled, right? So take note, however, that label is not just necessarily names, okay? It doesn't necessarily have to be like vertex names like A, B, C, D or the name of the person itself. It could be just a number, okay, or an ID or a Boolean value. So example of this of the Boolean value would be a healthy or a sick individual. So you can do away with the person's name. You're just interested whether he is healthy or sick. Okay, like for infectious disease spread na modeling, you could like for contact tracing. If A has been in contact with B and B has been in contact with C, you don't need to know what their names are. You could just give them an ID and then give them a Boolean value whether they are healthy or not, and then you could already do something with that. Okay, so it not labels are not necessarily names. You could put whatever label is necessary in your graph problem. Okay, so that is the friendship graph. So for graph applications, you can use this to represent any type of relationship, right? So road networks, okay, wherein your nodes would be the intersections and the roads itself would be the edges. Okay, you can represent the World Wide Web as a graph also, wherein your web pages are the nodes and then the hyperlinks or the links are the edges that connect them together. And then of course you have your social networks where people are linked together with relationships. Then you also have precedence constraints, so we'll see this later in the second half of the video. Okay, and maps in games. So if you're playing games with maps, underlying data structure for that one behind the scenes is usually a graph itself. Okay, so yeah, there's a lot of applications for graphs. Okay, so next, let's take a look at graph representations, because, well, as humans, we can immediately see the graph visualization, right? We can draw the nodes and link them with link them with edges, so we can see the graph pretty easily. But if we feed that to the computer, okay, we can't feed the image of the graph to the computer, right? So how do we represent the graph itself so that it would be usable by the computer, okay, by our program later on? So we will talk about graph representations. So we will talk about adjacency list and adjacency matrix. Okay, so these are the two main graph representations that we will use. Okay, so why is this important? Because the graph data structure that you will use has an impact on the performance. Okay, so whether you use adjacency matrix or adjacency list, depending on the type of graph that you have, that will affect your performance. Okay, so because one is more appropriate for some cases, and then the other one is appropriate for other cases. Okay, so let's start with the adjacency matrix. And I think we've already covered this before in ComSci 57, but we'll just review the adjacency matrix. Okay, so given that there are n vertices, an adjacency matrix is an n by n 0, 1 matrix. Okay, so the size is n by n, okay, and then it's a 0, 1 matrix. So if it's a 0, 1 matrix, the contents of the matrix is either 0 or 1. Okay, so you put 1 in xy, the coordinate of xy, if xy is an edge in the graph. Otherwise, you put 0. Okay, so basically this just answers whether there is an edge in that vertex pair. So for example, if you have 3 vertices, A, B, and C, A, B, and C, so if there's an if the graph is like this, A, B, C, so A to B to C, so if there's an edge from A to B, so you put 1 there, and then there's also edge from B to A, so you also put 1 there. Then A to C also has 1, so A to C to A also has 1 here, and then B to C has 1, same with C to B, and then the rest would be 0. Okay, so this is now your adjacency matrix. Okay, so the adjacency matrix quickly answers whether an edge is in edge xy is in the graph, because you can just check the for example, if is there an edge BC, so just go BC, and if it's 1, then there is an edge there. Okay, and you can also quickly update the graph. If there's an insertion or a deletion of an edge, you can just flip from 0 to 1 or from 1 to 0 if you insert or delete an edge. Okay, so it's pretty easy that way. So for adjacency matrix, it uses theta of n squared na memory because you're using an n by n matrix, so it's n squared. Okay, and it is efficient for dense graph. If there are many edges, then you can justify using up n squared memory, because anyway most of the n squared memory will have ones in there because there are a lot of edges. But if it's a sparse graph, there will be a lot of zeros, so it will not be as efficient. Okay, it would be wasteful for sparse graphs. Okay, now there are some variants that you could do for the adjacency matrix. If there are parallel edges, then the n3 would tell you the number of xy edges. So if there's a parallel edge from A to B, like two edges there, instead of 0, 1, you can put the number of edges. So you can put 2 or 3 or however many edges there are that connects x and y. Okay, if it's a weighted graph wherein the edges have weights, then you could also put the weight instead of 0, 1. Okay, so that you could already model the weight of the edge itself. And then if it's a directed graph, you could put plus 1, so the positive plus 1 if it's in the correct direction, so x going to y, and then negative 1 if it's y going to x. Okay, so if it's in the opposite direction, so like if it was something like this, like A, B, so if it was A, B, okay, so since it's going in the right direction, A, B will have plus 1, okay, but then B to A also has an edge, but it's in the opposite direction, so this is minus 1. Okay, does that make sense? So there is an edge here, but it's in the opposite direction, so you can annotate that with negative 1. Okay, so yeah, those are some of the variants. So that is adjacency matrix. Now next representation is it's called adjacency list, and in adjacency list you use linked lists to store vertex neighbors. Okay, so for each vertex you have an assigned linked list, and that linked list will contain the neighbors of that particular vertex. So it's pretty straightforward. I'll show you in an example later, but this time it would be slower to answer if the edge xy is in G, right, in the graph G, because earlier in adjacency matrix we just looked up xy's coordinate if it's 0 or 1, so that means that there's an edge or not in the graph. But in the linked list you will have to traverse the linked list itself. So if is there an edge xy, so you have to go for the linked list of x and then check in that linked list if there is y as a neighbor, right? So it would be slower to answer if the edge is present or not. However, it uses less memory than your adjacency matrix in general. So it uses m plus n, theta of m plus n memory. So m would be for all the edges, and then n would be for all the vertices. So I'll show you why in a while. So let's see this example, and let's just draw this one so we can see it in the next slide. 5, 4, 3. Yep, so this is our graph, and this would be the adjacency matrix and the adjacency list. So in the adjacency matrix we have the following. So we have 1, 2, 3, 4, 5 here. So since we have the 5 vertices, and then for the edges we have 1, 2, 1, 5. So that is here 1, 2, 1, 5. Then for 2 we have links to 1, 5, 4, and 3. So everything except itself has a 1. For 3, it's only connected to 2 and 4. And then for 4, it's connected to 2, 5, and 3. So that's 2, 5, and 3. And then for 5, it's connected to 1, 2, and 4. So 1, 2, and 4. So the rest would be filled up with zeros. And then for the adjacency list, it's also pretty straightforward. So it has, for 1, the neighbors are 2 and 5. So you write 2 and 5 here. For 2, the neighbors are 1, 3, 1, 3, 4, and 5. For 3, the neighbors are 2 and 4. For 4, the neighbors are 2, 3, and 5 here. And then for 5, 1, 2, 4. Okay, so this is just the linked list of the neighbors. So the size of this is n by n because, well, you have n vertices here and n vertices. So you have an n by n matrix. Okay, whereas this one is using n plus m na, what do you call this? Memory, because first of all, you need O of n for each vertex. So that is the O of n here. And then for each edge, that it's actually counted twice, right? Because each edge, like, so how many edges do we have? 1, 2, 3, 4, 5, 6, 7. But how many entries are there in total in the linked list? You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 7 edges, but there are 14 entries in the linked list. And why is that? Because for each edge, like 1, 2, this one will be considered in 2, 1, and then this one will also be considered in 1, 2. So we're actually logging each edge twice. So once for each vertex and then twice for each edge. So that's n plus 2m or O of n plus m. So that is why n plus m ang size sang memory of the adjacency list. Okay, so that is our first example. Let's take a look at the second one. For this one, go back to yellow. So let's draw this one again. 4, 2, 3, 5, and 6. But this time, this is a directed graph already. So 1, 2, 5, 4, 3, 6, and then a self loop. Okay, so given this graph, this would be our adjacency matrix here. So you'll notice that what will you notice? So for this edge, for example, 1, 4, so we have the entry for 1 to 4 with 1. And then for 4 to 1, it has entry -1 because it's in the opposite direction. And then for 1, 2, same thing. So 1, 2, we'll have +1. And then for 2, 1, it's the opposite direction, -1. Okay, so you do that for the rest. And then you'll notice that 6 has 1 here because there's a self loop. Okay, so the only thing that differs here is that there are negatives for the opposite direction in the adjacency matrix. Then for the adjacency list, it's pretty straightforward still. So for 1, it has neighbors 2, 4. For 2, has neighbors 5. For 3, neighbors 5, 6. But take note that this is only modeling the successors. So for 1, for example, you're only modeling 2 and 4 because there's an edge from 1 going to 2 and from 1 going to 4. We are not doing 4, 1, for example, because there is no edge from 4 going to 1. So we'll follow the direction for adjacency list of a directed graph. Okay, and then finally for the comparison, so if you want something that tests faster, so which one tests faster if the edge xy is in the graph? That would be adjacency matrix, because again, you can just look up the xy coordinate if it's 0 or 1, right? Faster to find the degree of the vertex, this would be adjacency list, because for adjacency list, you can just get the length of the linked list itself, and then you'll get the degree of the vertex. How many neighbors does it have? For the adjacency matrix, you will have to traverse the particular row of the vertex and find out how many of them are ones. Okay, or you'll sum up the row itself to get the degree of the vertex. Which has less memory on small graphs, that would also be adjacency list. Less memory on dense graphs would be adjacency matrix, but only slightly. So if it's dense, it's better to use adjacency matrix. If it's sparse, it's better to use adjacency list. Okay. Adjacency matrix also has faster edge insertion and deletion, because you can just again flip the zeros and ones quickly, right? If you're inserting an edge or deleting an edge. But in adjacency list, you will have to traverse the linked list and either insert it there or delete the neighbor, right? But in general, adjacency list is better for most problems, okay, because it uses less memory. Okay, so that's the comparison between the two. Okay, next we will talk about graph search, which is one of the two fundamental graph operations. So the two fundamental graph operations that we will discuss would be graph search and then later on path finding. So when we talk about shortest paths, we will do path finding. But for now, we will talk about graph search. Okay? So for the generic graph search, our input is a graph G, and then we also have a starting vertex, we'll call that S, and then the goal vertex F. So start and finish nodes. Okay? And our goal or our output is whether the goal vertex F is reachable from S. So that is our goal, right? Can we reach F starting from S? Okay? And we also won't explore nodes more than once so that we can finish the search faster. Okay? So as much as possible, only go through each node once. Okay? So our goal is to do this in O of m plus n time, or basically in linear time. Okay? So, okay, wait. So here we have our pseudocode for our graph search, generic graph search algorithm. So let's go through each line. So we will keep track of which nodes we've already explored, okay? And then we will keep something called a fringe, wherein we will get nodes from this fringe, okay? And initially, we will put the starting vertex S at the fringe. And then we will do this loop while the fringe is not yet empty, so meaning while there is still items in the fringe. So we will get a node from the fringe, but if that node is already explored, we will skip it, because as we've said, we will only visit each node once. Now, if that node that we got was already the finish vertex or the goal node, then we will return it, right? So we found it. Otherwise, we will add this node to the explored, since we've already visited it now, and then for each neighbor in the node we will add that neighbor to the fringe if it's not yet explored. Okay, if it's already explored, we will skip it, but if it's not, we will add it to the fringe. So this will add more items to the fringe, and then we will get another node from the fringe again. Okay, so we will do this until we've either found the goal or if the fringe is already empty. Okay, if the fringe is empty and we haven't found it, then we will return null because we did not find anything. Okay, so that is the generic graph search. Okay, you'll notice that the graph search, the generic graph search is underspecified, because we just said that we will get the node from the fringe, but we did not specify how do we select that node. Okay, so that is how the two graph search algorithms that we'll discuss differs. So we will do it in either breadth first manner or depth first manner. Okay, so either BFS or DFS. Okay, so for breadth first search or BFS, we will explore the nodes in layers. Okay, so for layer 1, we will do all of that, and then next layer, and then next layer, and so on. So we will use this, and it will run in O of m plus n time, so more or less linear time, and it will use a queue data structure. So remember, queue uses first in, first out. Okay? So for breadth first search, it's just the same as the generic graph search. The only thing that matters here, the only thing that differs here is that the fringe is now a queue. Okay? And then when we get an item from the queue, we will dequeue the a node, and then everything is the same. Okay? When we add items to the queue, we will enqueue the neighbor. So this is the only two things that differed. So when we get an item from the fringe, we dequeue, and then when we add items to the fringe, we enqueue. Okay? So that's the only thing that is different. So when is BFS usually used? So you use this when you only need to search part of the tree. Okay? And when the solution is known to be not far from the root, then you can afford to go layer by layer. Okay? However, the memory consumption of breadth first search is quite a lot. Okay? It has memory of O b raised to d, where b is the branching factor, or how many branches do you have, and then d is the depth. So how deep do you go? So the deeper you go, the more memory you are consuming, because you are actually keeping all of the previous layers in memory. Okay? So compared to DFS, as we'll see later, it consumes more memory. Okay? So saves the previous levels nodes, so it consumes a lot of memory because it's saving a lot of nodes, especially if you're going deeper and deeper at deeper levels. Okay. So that is BFS, and I'll show you how it works later after we discuss DFS. But for now, I'm sure that you're already familiar with the two, since we've already encountered this in ComSci 57. But we'll just do a review here. Okay. So for DFS, we will explore the graph as deep as possible. Okay. And we'll only backtrack if necessary. So if we hit a dead end, then we will go back and try another path. Okay. So this is similar to searching through a maze. Okay. If you're in a maze, then you just go as deep as possible, and then when you hit a dead end, go back and find another path. Right? So this will also run in O of m plus n time, but this time it uses a stack. Okay? Whereas BFS uses a queue, DFS uses a stack. Or if you use recursion, there is an implicit stack, but either way, it uses the last in, first out method. Right? So the last neighbor that you added, that would be the first fringe node that you will take out. So later on, we will see how that works for the depth first search. Okay? So for DFS, again, it's similar to the generic graph search. The only thing that differs is that the fringe is specifically a stack this time, and when you remove items from the fringe, you'll use the pop method of stack. Okay, so you remove the top item, and then if you add items to the fringe, then you use the push method of the stack, so you add items to the top. Okay, but everything else is the same. Okay, so when is DFS applicable, or when is it more when do you use it? So DFS is applicable when you need to search the entire tree. Okay, so when you need to search the entire tree, it's better to go as deep as possible, because what if it's found in the left part? Okay, so I'll show you an illustration. Okay, so if you need to search the entire tree, and let's say that the tree looks like this, then and so on, like this. Now, if the solution is found somewhere in the left part, if you go as deep as possible, you can find it easily, right? If this is the goal. But if you do it layer per layer, like in BFS, then it would take you a long time to reach the last layer, or the goal layer, right? So if it's DFS, you can reach this layer as soon as possible, as fast as possible. Okay, now if it's in the worst case wherein the solution is somewhere here, then you're not better off doing BFS. But basically, if you still do BFS, still the same, right? You're still going layer per layer until you reach this one. And then if you do DFS, it would also take a long time to reach this one, but that is already in the worst case. Okay, whereas BFS would be more applicable if the solution is shallow, right? What if it's somewhere in the third level lang? Okay, so if you go layer per layer, you could reach it faster. But if it's here and then you go depth first search, like you go deep as possible, it would take a long time before you reach this one. Okay, so yeah. So the other advantage of DFS is it only stores the list of parents of the current node, whereas in BFS it stores all of the previous layers nodes, but here only the parents. So the path from the root going to the current node, that's the only thing that it will save. So only few items, whereas in BFS it saves all the previous nodes, previous layers nodes, right? So if it's something like this, you will save more items when you're doing BFS the deeper you go. Okay, so it actually uses less memory than BFS, okay, because you're only storing parents of the current node. Okay, so that is one of its advantages. Okay, so let's take a look at how BFS and DFS will work given this example graphs. So okay, so for this one, for BFS, if we start with S, for example, so our first layer is S here, it would be S, and then our second layer would be going here and here, so this is the second layer. So we'll be going A and then B. And then for the third layer, A will go to C, B will go to C and D. So this is the third layer, C and D. And then finally, C will go to E, D will also go to E. So this is the last layer, E. Right? So this is your BFS per layer. Okay? If we were to go DFS naman, starting at S, S can go to A, okay? So S going to A, and then from A can go to C, okay? And then from C, it can go to B, so that is its first neighbor. Then from B, it can go to D, and then from D, it can go to E. So that is depth first search because you are going as deep as possible, right? So you started from S. It has two neighbors, but if we go through it alphabetically, it should pick A first. And then A only has one neighbor. Actually, it has two, S and C. But since S has already been explored earlier, then we won't explore it again, right? So we'll go to C this time. And then from C, it has three unexplored neighbors, B, D, and E. And then if we go alphabetical, then we'll just pick B. And then from B, it has only one unexplored neighbor, which is D. So it will go here. And then finally, the only unexplored neighbor of D is E, so it will go here. So that is depth first search. Whereas in breadth first, so starting from from S, it has two neighbors, A and B, so that would be added to the fringe. So A and B would be added next. From A going to C, and then B can go to also C or D, but C is already discovered, so we'll add that. And then from C can add E, same with D. So that is the layer by layer approach of BFS. Okay, how about this one? Okay, so for BFS, that would be A. So in the Q, so this is the Q. Maybe we'll add more space here. So we start with A, and then we'll add its neighbors, right? So we'll add B and C. So B and C would be included in our queue, and then A is already done, so A has been discovered, and then B and C. So you will go B will be dequeued first, and then when we dequeue B, we will add its neighbor D, right? So we'll add that there, and then after that we'll dequeue C, and when dequeuing C, we will add its neighbor E and F. So E and F here, and then after that D would be dequeued, but since it has no neighbors, don't add anything. Same with E, and then same with F. So dequeue. So basically the BFS order would be A, B, C, D, E, F, right? Pretty straightforward. And then for the DFS, we will use a stack, right? For our stack here, let's say that we start with A first, and then after A, we will add its neighbors B and C. So we can add C first. So A has been popped, right? And then C, and then B. So after that, B has been added on top. So B will be popped off, and then we will add the neighbor of B, which is D, on top. We'll add D. And then after that, D will be popped off since it's in the top. So we'll add D here. And then D doesn't have any neighbor, so we don't add anything. After that, we'll go back to the top, which is this time C. So we'll pop that off. So C is added here. And then we'll add its neighbors E and F. So F will be added first, and then E. After that, E will be popped off, no neighbors, so it's done. And then after that, F will pop off, no neighbors, so that's done as well. So this is now your order. So A, B, D, and then backtrack into C, then E, going back to F. Okay, so that is your DFS order. Okay. Finally, we have this one, and I'll just go through this quickly. So it's pretty straightforward na lang man. For BFS, that would be A, and then going to the next layer, BC. Okay, then the next layer, DE, and then FG, right? So this is the third layer, DEFG, and then from D you can go to H, from E you can go to I, J, and then K. So it's basically still A, B, C, D, E, F, G, H, I, J, K for the BFS order, right? But for the DFS order, that would be A, B, D, H, right? So you go as deep as possible, and then since it's done, go back. After H, we go to E, and then I. After that, backtrack, C, F, J, and then G, K. Okay, so again, that would be A, B, D, H, and then we backtrack, back here, E, I, backtrack again, C, F, J, G, K. Okay, so that is the DFS order. Okay, so yep. Now, the next thing that we'll discuss is something called tree traversals, and it's the process of visiting each node in the tree. Okay, so what would be the order of visiting nodes? Now, if you do DFS, or depth first search, there are three possible traversals. So you have the pre-order, post-order, and in-order. Okay, and then for BFS, there's only one way, which is level order. Okay, so we've also already discussed this in ComSci 57, so we'll just review it here. So for the DFS traversal, pre-order means that you have to visit the root first, and then the left subtree, and then the right subtree. So root, left, right for pre-order. Okay, and this is useful for copying trees because you need to copy the parent first before the child. So the root first before the left and the right. Okay, now for post order, it's the opposite. you have to do the left first and then the right before visiting the root. Okay? So this is now useful naman for deleting trees because you have to delete the children before the parent. Okay? So that the cleanup would be smooth. And then the third one is in-order traversal, wherein you traverse the left tree first, and then the root, and then the right subtree. Okay? So this is used in binary search trees. Okay. And then for level order, for BFS, it's just every node on one level before going to the next. So basically how BFS works. Okay? So let's take a look at how this will work for each na tree traversal. Okay. So for pre-order, so remember, pre-order is left. Pre-order starts with the root, right? So pre-order starts with the root, and then the left, and then the right. Okay? So if that is the case, how would we do it? I'll just use green here. So visit the root first, so that's A. Okay? And then the left subtree, so this one here. But for the left subtree, we also have to visit the root first, so that would be B. Okay? And then the left, which is D, and then the right, which is E. Okay? Then after visiting the left subtree of A, we'll visit the right subtree. But in this subtree, we will visit the root first, so that is C, and then the left, which is F, and then the right, which is G. Okay? So that is the pre-order traversal. Now, how about if we do the next one, which is post-order? Okay, let me just erase this one first. Okay, now that it's clean, we can write the post-order. So for post-order, take note that we have to do the left first and then the right before doing the root. Okay? So for this tree, instead of visiting the root first, we have to visit the left subtree first. Right? But in this subtree, we also have to visit the left part first. So we have to visit D first. So that would be D, and then the right, which is E, and then we can visit the root now, which is now B. So this would be DEB. Okay? After we finish the left subtree, we need to visit the right subtree. So we need to visit this first before the root, which is A. But for this subtree, we also need to visit the left first, so that would be F, and then the right, which is G, before the root, which is C. Okay? And then after the left and the right subtrees, we can now visit the root, which is A, here. Okay? So that is the post-order traversal. And then finally, let's go through the in-order traversal. So we'll go through it after I erase these markings. Okay. So next we have in order, wherein you need to go through the left first, and then the root, and then the right. Okay? So what would be the order here? So this is pre-order, post-order, next is in order. So for this one, we need to process the left subtree first, right? And then in this subtree, again, we need to process the left subtree first, so that would be D. After that, we need to process the root, so B is processed next. And then the right, which is E. So D, B, E siya. After processing the left subtree, we can now go to the root, so that is A, right? and then we go through the right subtree, which is this one. But in this subtree, again, we'll process the left first, so that would be F, and then the root, which is C, and then the right, which is G. So this is now the order. Okay? And then for the next one, which is level order, so I'll just use red so that I don't have to erase. So the level order, which is just basically BFS. So we'll just go through per layer. So layer 1 is A. The next layer is here, B and C. That would be the second layer, B, C. And the third layer would be D, E, F, and G. That would be the third layer here, D, E, F, G. Right? So that would be your 4 traversals. So pre-order, post-order, and in-order, level order. So if we remove all of these markings here, should be able to see the answers in the next slide. Okay. It's a lot harder to erase because you have a... I can't change the size of the eraser. Yeah, so just bear with me for a few moments. Okay, now that it's clean, you can go to the next slide. And yeah, we have the pre-order A, B, D, E, C, F, G. Post-order is D, E, B, F, G, C, A. In order is D, B, E, A, F, C, G. Then the level order is just A, B, C, D, E, F, G. Okay? So yeah, that's the 4 orders for the 3 traversals. Okay, so that is where we'll end our first part. So to review, we discussed graphs. So they represent pairwise relationships between objects. Okay, we discussed the representations. You can use adjacency matrix or adjacency list. And then we did breadth first search and depth first search. So BFS goes per layer and it uses a queue, whereas DFS goes as deep as possible and then it uses a stack. We also went through the 3 different traversals for DFS. Pre-order, so for pre-order it should be root, left, right, and then post-order is left, right, root, and then in order is left, root, right. Okay, and then there's also the level order traversal for BFS. Okay, so this is where we'll end part 1, and then part 2 will follow shortly. Okay, so we are now in part 2 of our graph algorithms lecture, and in this part we will be applying BFS and DFS to 2 problems, namely connected components and topological sorting. Okay, so let's start with connected components. So let's say that our given graph G is an undirected graph and we don't know whether it's connected or not. Okay, the connected components of the graph are known to be the pieces of the graph. So if it's a connected graph, meaning it's one whole graph, then there's only one component. But if it's disconnected, okay, there are some vertices or groups of vertices that are isolated from each other, then we will have multiple connected components. Okay, so formally, in connected components, we say that vertices U and V are connected if there is a path from U to V and from V to U. Okay, so if the 2 vertices are reachable by using a path, then they are connected and they are part of the same component. Okay, so a connected component is just a group of vertices such that all vertices are reachable to each other. Okay, or from each other. So there is a path from one vertex to any other vertex in that connected component. Okay, so for undirected connectivity, that means that we are given an undirected graph as our input. Okay, and our output would be to find all the connected components of that graph. Now, if we were given the graph visually, it would be quite easy to see what the connected components are, because just looking at this one, then it's easy to see that there are 3 components to the graph, right? So this one is one component because all of the vertices here are connected. So you can reach A to C, A to E, A to G here, A to I, and then for the rest of the vertices, you can also reach the other vertices. And then this one is another component here, B and D, because they can reach each other through this edge. And then the third component is this one, because you can reach F to H and F to J, and then H to F, H to J, then same with J, J to H, J to F. Okay, so we have three components in our given graph. And again, as I mentioned, it's easy to see visually. But for the computer who cannot see the visual representation, but it's only given the adjacency list or adjacency matrix, it might not be as straightforward, right? So it might not be as easy to give the connected components just from the adjacency list or adjacency matrix that's given. Okay, now why are we interested in graph connectivity? So some applications of this problem include network connectivity, clustering, and modeling disease spread. So for network connectivity, you'll try to see if there's only one connected component. Okay, if there are multiple connected components, then your network is probably disconnected. Okay, and then for clustering, you would want to cluster or group some items together. Okay, so that's the connected component. And then for modeling disease spread, the same thing. If some people are connected in one component, then probably one infection in that group could spread the disease faster, right? So you need to identify certain clusters or certain components. Okay, so for undirected connectivity, what we'll do is we will use the existing BFS that we know, so breadth first search, to uncover the connected components in our undirected graph. Okay, so what we will do is initially all nodes are unexplored, so they're untouched for now, and then the components of each node is set to empty because we don't know what their components are yet. And then for each node V in the graph, so it doesn't really matter what the order is, you could start with any node, you'll still get the same results anyway, as long as that vertex has not been explored yet. Okay, because remember that for BFS we need to only explore once, right? So as long as the vertex hasn't been explored, then we'll do a BFS traversal starting from that vertex V, and everything that's reachable from that vertex V would be part of the components of the node. Okay, so everything that's reachable from V would belong to the same component. Okay, and after doing this for all nodes, or if all the nodes have already been explored, then we will return the different components. Okay, so it's pretty much it. Okay, so what would be different from the basic BFS and then the BFS traversal? So it's more or less the same, but we will just skip if the node is already explored, and then otherwise we will mark it as explored. And then for each neighbor, we will also skip if it's explored, and then we'll enqueue each neighbor. So more or less the same with the BFS that we have seen in the previous part, right? So yeah, and the only difference is that we are returning what we have explored, and that means that these are the nodes that we reached from the vertex, the starting vertex S. Okay, and those reachable nodes from S would be part of the same component. Okay, so for the analysis, running BFS on the graph starting at V will uncover vertex V's connected component. Okay, so all vertices that are reachable from V would be part of the connected component. And so in this algorithm, we will visit the nodes once, and we will also visit the edges once. Okay, why is that? So let's go back here. So we will only visit the nodes once because for each node V in G, and we need to make sure that V hasn't been explored yet. So if it's already explored, we will just skip it, right? So we are assured that each node will only be visited once. And then in the BFS traversal, we will also go through each edges as long as that edge or the neighbor hasn't been explored. We will try to process those edges. So all edges will also be processed at least once. Okay, so yeah, so that's O of n and then plus O of m in total. So the running time would be O of m plus n, okay, because we'll visit each node once and then each edge once. Okay, and then for the memory, we will take O of n memory because we are using a queue for the BFS, and the queue could hold up to n nodes, at most n nodes, right? So yeah, it would be O of n ang memory niya, extra memory. Okay, so let's see a simple example of how BFS would uncover the connected components of this graph. Okay, so let's see. That's this graph. So we'll start our queue at A and then run BFS starting at A. So A will uncover E and C, right? Because those are the two neighbors. And then from C, since it's the next in line, you don't add other neighbors because E is already there. And then E would be processed next, and it would add the neighbors G and I. And then after that, G would not add anything, I would also not add anything. So since the queue is empty, we'll go to the next one. So if, let's say, we are going through this in alphabetical order, so after A, we'll go to B. So we'll in queue B. And then from B, run BFS again. It will discover D. And then after that, there's no more neighbors to add. So our queue is empty again. So we'll go through the next one, which is C, but C is already done. D is also done. E is also done. So we'll go to the next one, which is F. So at F, we will uncover H and J. And then from H, there's nothing to add. And then from J, there's nothing to add. So we have also discovered the three nodes that are part of the same component. So now, we are done with the connected components. So earlier, when we started at A, it uncovered the nodes that are in its connected component, which are A, C, E, G, and I. And then when we started at B, it uncovered B, D. Okay, and then starting at F, F, H, J. So these are the three connected components that were uncovered by BFS. Okay, so that's it. That's pretty simple, right? Just run BFS at the nodes, and then whichever nodes it uncovers or discovers during that run of BFS, that would be part of its connected component. And then you go to the next node that hasn't been visited yet, and then run BFS again, and so on. Okay, so that is undirected connectivity. Let's now go to strongly connected components. And how is this different from the previous one? Okay, so it's also connected component, but this time, this is for directed graphs. Okay, earlier we were given an undirected graph, but this time it's already a directed graph. So the edges will have direction. Okay, so for directed graphs, we say that it's a strongly connected component if all edges in the path from U to V follow the correct direction. So strongly connected ang two vertices, U and V, if there's a path from U to V and V to U, and it follows the correct direction of the edges. Okay, so meaning if it's going forward, then you're following that one. It's weakly connected if some edges in the path from U to V does not follow the correct direction. So we could get from U to V, but only if we thought of it as undirected, meaning we did not follow the direction of the path. Okay, so let's say, for example, A, B, C, and then A. So A to C is strongly connected because there is a path from A to C following the direction. So you're following the correct directions here, right? And then there's also a path from C to A following the correct direction. But what if it was something like this? A, B, C, and then like this. Okay, so what would be, or even without this one, maybe, okay, what if the graph was only like this, A, B, C? Okay, there is a path from A to C that follows the correct direction, right? A going forward to B, and then B to C. But from C to A, there is a path if it was undirected. But if it doesn't follow the correct directions, right? So it's going backwards here to here. So that is only weakly connected because you don't follow the correct direction. Okay? So that would be our second problem, strongly connected components. So strongly connected components are maximal regions of strongly connected vertices. So the maximum group or the group of vertices that's as many as possible, okay, such that all pairs of vertices are strongly connected vertices. So that just means that the two vertices U and V are in the same component if there exists a path from U to V and from V to U legally. And by legally, we mean that it follows the correct direction of the edges. Okay? Since this is a directed graph. So, for example, in here, so we're given this directed graph. Unlike earlier, wherein it was just undirected connectivity, it's not as straightforward to find the strongly connected components, right? So you can try to pause the video for now and try to figure out on your own what the strongly connected components are. Okay, and again, it means that there's a group of vertices such that each vertex pair can be reachable from each other following the legal path or legal direction. Okay, so let's try to encircle some of the strongly connected components. So there is a triangle here from C to G, G to H, and H to C. So that seems like a candidate for a strongly connected component, right? Because you can get from C to G, C to H, and then from H to C, H to G, and then same from G to H, G to C, all following the correct directions. Okay? So that seems like one group. Now, could we have added D as part of that group, as part of the component? Because again, this should be a maximal region, right? As many vertices as possible. Maybe we could, but there's only a path from G to D, but you cannot go from D back to G or to C or to H, right? So D is not part of that connected component. And same thing for J and I. Okay, if we add J as part of the connected component, you can only get from H to J or from H to I, but not going back. Okay, so it's only this three that's part of the connected component. And then for this one, same reason. So you could add A to F, F to E, E to A. So that is also one connected component. Now, if we added D there, it won't be a strongly connected component because D only has a way going into E but not from E going to D, right? So it's not, D is also not a part of the strongly connected component. Now, how about here? There's also another triangle here, I, B, and then J. So this is another triangle. So is this the strongly connected component? Maybe, but take note that it should be maximal region, right? So the strongly connected component is actually this 4 here. So because from I, you can get from I to K following this path, I to B following this path, okay? I to B, and then from I to J following this path. And then from K, you can get from K to B, K to J, and then K to I. And then from B, you can go to J, go to I, then go back to K. And then lastly, from J, you can go to I, K, and then back to B. So all vertex pairs are reachable within each other following the correct direction. Okay, so this is the strongly connected component. And then finally, this one is left alone, so that is also another component by itself. Okay, so those are the four strongly connected components. So compared to undirected connectivity, is not as straightforward to find, right? And it's also not as straightforward to do in an algorithm. So how will we try to uncover our strongly connected components? Before that, why are we interested in this problem? So what are the applications? So one application could be in the food web. So you could try to find the subset of species with common energy flow. So that means that they are looping the energy from one to another. And then there's also software module dependency, wherein if this module depends on another module, and then this module depends on another module, so you can package strong components together so that they are already since they are dependent on each other, you can just put them in one component. Okay, so those are two applications of strongly connected components. So okay, now how is this related to DFS? So let's try to run DFS on this graph, and let's try to run it at three different starting points. So if we started at A, what would A uncover in the DFS? So from A, it will go to F, then from F it will go to E, and from E, well, wala na because we've already uncovered A, and then that's it, right? So it uncovered this strongly connected component. So that is if we started with A, right? But what if we started with B? We started at B, ang DFS. So if at B, DFS would go to J, and then from J it would go to I, from I it would go to F, from F it would go to E, and then to A, and then since this is a dead end, it will go back to E, back to F, back to I, and then from I to K, K to B, and then go back. Wala na. So that's it. But you'll notice that it uncovered this two. So it kind of merged the two connected components, right? We know that the answer should have been this plus this, right? Those are the two connected components. But if we started our DFS at B, it merged the two strongly connected components together, which is bad, right? Now, it's even worse if we start at C. Why is that? So if we start at C, C will go to G, G will go to D, D will go to E, E will go to A will go to F, then F will go to, well, so backtrack, and then from G it can go to H, from H it can go to I, from I it can go to K, to B, and then to J. So it actually covered or traversed everything into one component. So it merged everything, right? So that is really bad because we know that there should have been 4 different components, but if we start at C, you will just uncover one component, right? So this just means that if we start the DFS at the right vertex, we will find the correct strongly connected component. And if we start the DFS at the wrong vertex, then we will get the union of multiple SCCs. Okay? So it's important for us to start the DFS at the correct vertex. Okay? So we will have to do a pre-processing step, okay, to find out which vertex should we start our DFS. So the SCC problem was there are 2 algorithms that use DFS to solve the SCC problem. So one of which was Tarjan's algorithm, created by Robert Tarjan in 1972. And the other one was Kosarajus algorithm, created in 1978 by Sambasiva Rao Kosaraju. So we will discuss Kosarajus algorithm in this lecture. So both algorithms use DFS. Now for Kosarajus algorithm, he uses two passes of DFS. So he uses two DFS runs. The first one is the first DFS allows us to figure out where to start our DFS later to uncover the right SECs. Okay, and Kosarajus algorithm can compute SECs for a directed graph in O of m plus n time. Okay, so still linear in terms of edges and vertices. So this is the pseudocode for Kosarajus algorithm. So let's try to analyze this one. So the first thing that we'll do is we'll create the reverse graph of G. The reverse graph is basically just the graph itself, but with the edges reversed. So if your original graph has an edge going from A to B, in the reverse graph, the edge would be going from B to A. So you just reverse all the directions, okay? And then what we'll do is we'll run DFS on the reverse graph first, okay? And then what we will do is we will label the nodes based on the result of our DFS on the reverse graph. Okay, so we will call DFS label. So we will see later on how this works. And then after that, after we have labeled the nodes, we will run the second DFS, but this time on the original graph. Okay, and then we will process each node in the decreasing label order. So the labels that we created on the first DFS is important because that would be the order that we will follow later. So we'll follow it in decreasing label order. So if there are n vertices, we will start at vertex labeled n and then going down to 1. Okay, and then as long as that vertex hasn't been explored yet, we will do the DFS traversal, and whatever nodes it encountered during that traversal, that would be part of its strongly connected component. Okay, so yeah, that's Kosarajus algorithm. And for the DFS label, basically what we will do is we will add a label whenever it has been when it reaches a dead end. Okay, so whenever it reaches a dead end, we will add that label and then increase the label. Okay, so I'll show you what we mean later, but more or less everything else is the same as our normal DFS. Okay, for the DFS traversal, it's also the same. Nothing really is different. We'll just do the same traversal. Okay, so for Kosarajus algorithm, the first DFS is done to compute the ordering of the nodes. Okay, and we will do this again for the graph, for the reverse graph, or the graph G with edges reversed. And then the second DFS is when we compute the strongly connected components following the decreasing node order computed earlier in the first run of the DFS. Okay, so the SECs would be the nodes with the same label. So okay, before okay, so to analyze this one, to analyze the running time, so first when we create the reverse graph, that would run in O of m because we will just go through each edge and reverse them, right? So that would be O of m. The first DFS would be O of m plus n because, as we mentioned, DFS runs in m plus n. Same with the second DFS, it's also m plus n. So therefore the total running time would be O of m plus 2 times O of m plus n, which is still in O of m plus n, right? And for the memory, it uses O of n running time because we use stack in the 2 DFS, and the stack could accommodate at most n nodes because we're pushing the nodes to the stack, right, when we're doing DFS. Okay, so it's still linear time and it has O of n memory. Okay, so let's now go through the example. So if this is our graph, the graph reversed would look something like this. Okay, so again, from here, it becomes reversed. So all of the edges have reversed directions. Okay, and let's, so if this is our graph, we will reverse all of the edges, and then we'll run DFS here. So from A will go to G, and then G will go to D and I. So D or I, so we'll process D first, and then from D, it's a dead end because D doesn't have any neighbors that hasn't been visited yet. So once we reach a dead end, we will label that as 1, okay? Because our current label is 1. We haven't labeled anything yet. So it's the starting label, 1. Then after that, we will go to the next one, which is I. And then from I, we'll go to F. From F, it will either go to C or H. And then if we do the tiebreaker and follow the alphabetical, so we'll go to C first. So from C, it also is a dead end because there are no more neighbors after C that hasn't been explored yet, right? So since it's a dead end, we will label this as 2. Then after that, from F, you can go to H, right? So from H can go to B, and then from B, it can go to E. And then E is a dead end now because it cannot go anywhere. So we will label this as 3. And then going back, the stack top is now B. So from E, we backtrack going back to B, and B is now also a dead end because there are no more neighbors to add. So after that, it will backtrack again going back to H, and H is also now a dead end, right? Because no more neighbors. And then backtrack, F is also a dead end, so it's now 6. And then I is also a dead end, so it's now 7. G is also a dead end, so it's now 8. And then finally, A is now a dead end since it's also has no more neighbors to add, so it's now 9. So after the first run, we now have the labels for our nodes. So we will put it back to the original graph. So we'll just reverse the directions back, and then we will run DFS again, but this time starting from the highest label, so decreasing label order. So we'll start at 9. Okay, so from 9 we would uncover D, and then from D it will uncover G, and then after that it's done, right? So since you cannot add any more items after G, then that is done already. Okay, so after that you'll go to a label 8, but since G is already explored, we'll skip that. So it will go to the next one, which is 7 at node I, and then at I it will go to C, and then go to F, and then from F no more, right? So we're also done with DFS starting at I. So from 7 it will now go to 6, but 6 is also done, so it will now go to 5. It will start at H. From H it will discover E, and then B, and then dead end. So from 5, 4 is also done, 3 is also done, 2 and 1 is also done. So we have now discovered our 3 connected components, ADG, ICF, and then HEB. So every time you start a new DFS run, you will have to create a new connected component, strongly connected component. Okay, so that is SEC. Okay, so going back here, so this was the label on the first DFS on the reverse graph, and then by doing the second DFS, we will uncover the strongly connected components. Okay, so let's see one more example. Maybe we'll start, maybe we'll do the same one, but what if we started our graph at I, or our DFS at I, or maybe at what was it again? F na lang. F. Maybe at F. Okay. If we start at F, so we'll reverse everything, and then F goes to C or H, and then from C it will go to I. From I, no more, so that's a dead end, 1, and then go back to C, also dead end. From H can go to B, E, and then H. E is a dead end, so go back. B is a dead end, H is a dead end, and then F is a dead end. After that, maybe we'll start at A again, and then goes to G, D, D is a dead end, G is a dead end, A is a dead end. So after this, we'll start still at A, then uncover that, 6, uncover that, 5, uncover that. So we still got the same components even if we started our initial DFS at F. So the starting point doesn't really matter because it will uncover the same SEC anyway. Now, what if we tried this one on the graph that we saw earlier? Okay, so earlier we saw that if we started at C, it will uncover everything, right? So if we start at C, what would have happened? Now, we will do this instead on the reverse graph. So on the reverse graph, C would uncover H and then G, and then G would be a dead end, so that's 1. And then H would also be a dead end, so that's 2. C would be a dead end, so that's 3. After that, maybe at A, so A would go to E or K. So because it has edges going to E and to K. And then if we go to it alphabetically, it will go to E, and then from E, it can go to D or F. So maybe it will go to D first, and since D is a dead end, this will be number 4. And then F can still go to I, and then from I, will go to J, and J can go to B. B can go to K, because K hasn't been discovered yet. It has only been added to the top, but it hasn't been uncovered. And then K is now a dead end because it doesn't have any neighbors, right? Then from K, go back to B, also a dead end, go back to J, go back to I, go back to F, go back to E, and back to A. So now that we have the labels, we will start our DFS at 11, which is the highest, right? So start at A, it will do the DFS this time on the original graph. So A to F, F to E, and then that's it. 11, 10, 9 is done, so we'll go to 8, which is I. So I go to B or K, then if it's at B, it will go to J, J, backtrack, it will go to K, and then there's nothing else. So after that, 8, 7, 6, 5, and then the fourth one is D, but D doesn't have any neighbors that are hasn't been explored yet, since this one is already explored, so we'll stop there. After that, we'll go to 3, which is C, G, H, and then those are the 4 components, strongly connected components of the graph as we saw earlier. Okay, so that's it for strongly connected components. And finally, our last topic is called topological sorting. Okay, what is topological sorting? So topological sorting is the sorting of vertices of a directed graph such that all directed edges only go forward. Okay, what do we mean by this? So you're trying to rank or sort all vertices, so you're trying to order them in a way such that all edges U to UV, okay, for all edges UV, the rank of U appears before the rank of V. So U is before V. Okay, so if U to V is a edge, and that means that you have something like this, right? So U, V, if this is an edge, in the ranking, U must appear before V. So that is the topological sorting, and this is for all edges. Okay, it cannot be that V appears before U, because if that's the case, one edge is going backwards. All edges should go forwards in this case. Okay, so yeah, for this one, halimbawa, we could sort it like this, SVWT. So you'll notice all edges are going forward, okay, or SWVT. Okay, if it's SWVT, still all edges are going forward. Okay, so you could have multiple topological sorting depending on the graph. Okay, now topological sorting only works for directed acyclic graphs. So we know that the input that we have is directed, right? Because we need to follow the direction of the edge, but it also needs to be acyclic or acyclic. So there should be no cycles, okay? Because cyclic graphs cannot have a topologically sorted version, because if there is a cycle, then one vertex has to go back to the other vertex, and therefore it cannot have a proper order, right? So for example, if there is a A going to B, going to C, and then going back to A, so there can't be a topological sorted version of this, because if you do A, B, C, then one edge would be going backwards, right? So if there's a loop, it can't be topologically sorted. So if there is a cycle, it would be impossible to set the precedence of the nodes, right? Just like, for example, if you've seen this already, the Penrose stairs. So A seems like the top because it goes down to B, then B goes down to C, then C goes down to D, but D also goes down to A. So we don't know which one is the highest level of the stairs, right? So it's impossible to set precedence. Okay, so why are we interested in topological sorting? So some applications include precedence constraints, like course prerequisites in the course, for example. So you need to take ComSci 57 before ComSci 123, and then ComSci 123 before ComSci 142. So how do you order them such that all the prerequisites are done before the required course? Okay, and then for Java classes, you could also use this to uncover cyclic inheritance, right? So if are the classes ordered in such a way that there should be no the inheritance is correct, right? So A must be a superclass of B, and then B is a superclass of C. But then if C is a superclass of A, then there is a cyclic inheritance, so it's not possible. Then same thing for circular reference in spreadsheets. So you can also use topological sorting for this one. Okay, so this one is an example of a precedence for course prerequisites. So for example, 11 is a prerequisite for 21, 21 is prerequisite for 22, and 56 prerequisite for 57, 57 is prerequisite for 141, then 21 and 57 prerequisite for 123, 123 is prerequisite for 142, something like that. Okay, so yeah, so for the topological sorting, we will also use a DFS solution. Okay, if the graph is a DAG or directed acyclic graph, then we are guaranteed to find a topological ordering. Okay, so all DAGs have a topological ordering, and we can compute this topological ordering in O of m plus n time using the DFS. So how will we do it? So the idea is any DAG has at least one sync vertex. A sync vertex is a vertex or a node without any outgoing edges. Okay, so what do we mean by that? If it's a sync node or a sync vertex, then it only has edges going in, right? But there are no edges going out. Okay, nothing going out. So it's a sync because it basically everything is going into that node, but nothing is going out. Okay, why is this always true, that it has at least one sync vertex? So the reason for that is because if all vertices had an outgoing edge, there is bound to be a cycle. And since it's acyclic, right, and a directed acyclic graph, then there should be one vertex that doesn't go out or doesn't have any outgoing edges. Okay, so that is a property of directed acyclic graphs. There is at least one sync vertex, because otherwise it would just form a loop, right? So now we don't want our edges to go backward, because that would be a violation of the topological sorting. So that means that the vertex with outgoing edges cannot be the last. Okay, so if it still has outgoing edges, it can't be the last, because if it's the last, then its outgoing edges would be going back, right? So we can't put vertices with outgoing edges at the last part. So what vertex could we put at the last part? Well, it's simple. It should be the sync vertex. The sync vertex should be at the last because all the edges are only going in but nothing is going out, right? So it's safe to put the sync vertex at the last place. So that is what we will do. Okay? So if V is our sync vertex of the graph, then we will put the rank of V as the last. So N, meaning the last label, okay? Because N is the number of vertices, right? So it's the last number. And then we will recurse. We will do this again, this time on the graph without the sync vertex that we just labeled as N. Okay? So we will call this the residual graph, the G minus that vertex. So the residual graph is the remaining graph if we remove vertex V and all edges associated with it. So remove V and all edges connected to it, then that would be the residual graph. Okay? So after we remove vertex V, some vertex with outgoing edge going to V may now become the new sync vertex in the residual graph. So we'll see this later. Okay? So at each step, when we remove a vertex, we will uncover a new sync vertex naman. Okay? So after we remove that vertex naman, it will create another sync vertex and so on until we have labeled everything. Okay? So why does it work? Removing a DAG's sync, by removing the sync vertex, you are sure that the residual graph is still a DAG. Okay? It's still a cyclic because you can only create cycles by adding edges and not removing them. And since you're just removing edges, then you are sure that the remaining graph is still a cyclic because you're not adding cycles, right? You can only create cycles if you add more edges. But since you're only removing, then you are sure that the residual is still a DAG. Okay? And we always get the sync vertex per recursion. So we will always get that sync vertex and then remove it again and then continue with a smaller graph which also has another sync vertex created. Okay? So for this one, what would happen here? What would be the sync vertex in this case? So the sync vertex here is T, right? So let me make this red, or yeah. So the sync vertex here is T. So we'll remove T and we'll put it at the last. Now after we remove T, so this will be removed, this will be removed. V and W are now sync vertices as well because they no longer have any outgoing edges, because if we remove these two edges here, they won't have any outgoing edges as well. So we could have placed V, or if we placed W, that would have been acceptable as well. And then if we remove V, this would be removed. So after that, W would be the only remaining sync. So that would be W, and then when you remove W, S would be the only remaining sync, and that would be the topological ordering. Now, if we chose W first, then this would have been removed, and then V would have been the next sync, and then after that, it would have been S. Okay, so there are two possible topological sortings for this one. Okay, so putting all of that together in a pseudocode, this is how it looks like. So all nodes are initially unexplored, and then the rank would be blank. Okay, so the current rank is N, so meaning we start from the biggest number and then going down. So we are decreasing. And then for each node V in the graph, if V is not yet explored, then we'll do the DFS traversal. Okay, and this will uncover your sync vertex, because the last part of the DFS traversal, wherein you reach a dead end, that would mean that it's already a sync, right? Because there is no longer any neighboring vertices that you can go forward to. So you do the DFS traversal, and then you rank place the rank there until every node has been ranked. Okay, so what would be the difference here in the DFS traversal? So every time you reach a dead end, you just put the rank and then subtract. So that would be from n, and then n minus 1, n minus 2, and so on, going down to 1. Okay, so that's the only difference. So for the analysis, we always try to find the sync vertex using DFS. So this is when we reach a dead end, and we visit the nodes once in the vertex in the run, and then visit edges once, O of m. So why is this the case? So going back here, this one is visiting each node once, right? For each node v in g, if v is not yet explored. So every time we've explored that node, we will not explore it anymore. So that means that each node will only be processed once. And then in the DFS traversal, we will look at all the neighbors that are unexplored. So we'll also look at each edge at least once. Okay, we won't revisit it again if it has already been visited already. Okay, so all in all, the running time is O of m plus O of n, so that's still O of m plus n, which is the running time of DFS. Okay, and then for the memory, still O of n, because we're using a stack when we run our DFS, which could hold at most n nodes. Okay, so let's see this in an example. If it was the earlier example that we saw earlier, the simple one, so start at S. If we run DFS, so S, go to V or W. From V, it can go to T, but then T is already a dead end, so that would be label 4. And then going back, backtrack to V. V is also a dead end, so it will be 3. And then from here, we can go to W, but W is also a dead end now, so it becomes 2. And then finally, S is labeled 1. So this is the topological sorting. So S, W, V, T. Okay. How about for this one? I think this is graph 2. Okay. So if we start at A, start our DFS at A. So from A, it will go to F, and then F is already a dead end, right? There's no other nodes that we have, and you'll notice that F is a sink, right? Only edges going in, but no edges going out. So F is a dead end, so we will label this as, wait, how many nodes do we have? We have 6, so this is number 6. And then from A, going back, it's also a dead end because there are no more neighbors, so that would be 5. And then, since there are no more nodes in the stack, we will just go through it in an alphabetical manner. So we'll go with B, and then from B, it's also a dead end because A has already been explored, so we'll label this with 4. And then next is C. From C, it's also a dead end, so it's 3. From D, it's also a dead end. E is also a dead end. So that is your ordering, E, D, C, B, A, F. Now, let's try to see if this is indeed a topological sorting. So E, D, C, B, A, F. So there is an edge going from D to B and D to C. So D to C, D to B. From E to C, E to F. So E to C and E to F. And then B to A, and then A to F. So all of the edges are going forward. So this is a valid topological sorting. Now, for this graph, we started with we started at vertex A, right? But what if we started at a different node? What if we started at B, for example? So if we start at B, what would have happened? Now, if it was B, we'll run DFS, so B, A, F, then F is a dead end, so this is 6, A is a dead end 5, B is a dead end 4, and then the same thing will happen, C is a dead end, D, E is a dead end. So it's still the same result that we have. Okay, so yeah, that's topological sorting. So it doesn't really matter where you start your DFS, it will still uncover the sync node when you reach a dead end. Okay, so that's it. Yeah, so that's it for this lecture. So to review, we discussed BFS. We applied BFS to undirected connectivity. So if the graph is undirected, you can just run BFS to uncover the connected components. It's pretty straightforward, right? And then we used Kosorajo's algorithm, which uses two runs of the DFS to uncover strongly connected components. So the first DFS, we run it on the reverse graph to uncover the labels. Okay, so this order will be used on which starting vertex should we use for the DFS in the second run, and then the second run would of course uncover the SCCs itself. And we also use DFS for topological sorting. So run DFS starting at any vertex, and then once you reach a dead end, then that is a sync node, so you label that as the last one, and then continue until every node has been labeled. Okay, so that's it for this video. If you have any questions, please don't hesitate to ask, and I will see you in the next